In this section, we will present a tutorial on orthogonal frequency division multiple access as implemented in IEEE 802.16-2004 and IEEE 802.16e-2005. We'll focus on the physical layer with some discussions on the Mac, but the idea is to give a full, complete description of all the technical aspects involved with OFDMA. Let's give some history. IEEE 802.16 was published on December 2001. It was the original fixed wireless broadband air interface for 10 through 66 gigahertz, and also it was only line of sight, but it was a point-to-multipoint system, and also supported TDD and FDD, and the following and subsequent 802.16-2004 and 802.16-2005 refer to this document. IEEE 802.16a was published in January 2003. This was a major development since it extended the spectrum to 2 to 11 gigahertz, which included unlicensed bands. Also, very importantly, it was targeted to non-line of sight point-to-multipoint applications like last-mile broadband access, and it introduced OFDM using 256 point FFT and variable bandwidths, and also it introduced OFDMA, a key technology for multiple access. So 802.16a cover multipoint links, line of sight communication with a central base station. 802.16a also includes single carrier as well as OFDM and OFDMA. The line of sight links can either be single carrier or OFDM or OFDMA based, but the standard also supports non-line of sight. For example, shown here is a laptop. As you can see, there is no line of sight, but we can still achieve reliable communications using OFDM and OFDMA in non-line of sight situations with 802.16a. 802.16d, or more appropriately referred to as 802.16-2004, included a revision, a project authorization request, and importantly includes the WiMAX system profiles and some additions for support for 802.16e. 802.16e-2005 was published in October 2005 and supports mobile wireless devices for broadband for high vehicular speeds and also in licensed bands from 2 to 6 gigahertz. It also supports roaming for portable clients within and between service areas. In the case of 802.16e, as you can see, high-speed vehicle motion is also supported, non-line of sight is supported, communication within urban environments is also supported, and many additional additions have been added to 802.16-2004. The original work on orthogonal frequency division multiple access could be attributed to the paper by Sari and Karam back in 1998, and they also later referenced an important paper from Jacobson, Bingham Fan, and Cioffi at Stanford. And this particular paper deals with the synchronization from multiple subscribers, but the actual OFDMA application was developed by Sari and Karam. Should point out that the main document that details the OFDM and OFDMA is the IEEE 802.16a document. So in the following, I will refer to 802.16a, although when we talk about actual deployment, we need to talk about IEEE 802.16-2004, or in the case for mobile communications, IEEE 802.16e-2005. But since most of the material is available in the IEEE 802.16a, many times in the presentations I will refer to IEEE 802.16a. So you can actually go to that document in order to get more detail. To discuss OFDMA within a metropolitan area network, or say 802.16a, in general, these two diagrams, although simplified, will be used to discuss many aspects of OFDMA, and also a lot of the issues that are involved. Here we show a base station with multiple subscriber stations. In this case, assume that the subscriber stations could be fixed, for example, within buildings, and the base station could be in a high-rise building, central location, and these could be other buildings or homes which are subscribing to the network. Here we show the situation where you have a downlink from the base station transmitting data to the subscriber stations. Also, in this diagram, we have purposely shown the situation where the subscriber stations could be either close, far, or within medium range of the base station. It takes a while for it to reach a particular subscriber. For example, it may take 200 microseconds or 150 microseconds to reach one particular subscriber and less than 20 microseconds to reach a near-end subscriber. So subscribers that are on the edge of the network may take well over 100 microseconds compared to subscribers that are close by. An issue that arises is during the uplink. If we look at the uplink situation, each subscriber would transmit data to the base station. And of course, we are going to be talking about, in this case, time division duplex. And we would like for all subscribers to transmit such that all of their transmissions arrive at the base station at the same time. In this situation, we have to do some synchronization between the base station and the subscriber stations to accomplish this. Let me repeat, what we would like to have is that when the subscribers transmit during an uplink transmission to the base station, that the signal from all subscribers arrives at the same time or within a very small time window simultaneously at the base station. Another issue that arises due to the fact that these subscriber stations are spaced out at different distances to the base station is the fact that we would have to do some power control. Otherwise, subscriber stations that are close by can transmit with high power, and subscriber stations that are far away to the base station might receive signals from them which are lower power. In this case, the close-in subscribers would dominate and cause a lot of interference into the carriers, as we will describe, of the far-away subscribers. So within a network like this, we will have to provide a mechanism for power control. By power control, we mean that the base station has to communicate somehow with the subscriber stations and adjust the subscriber station's power level such that they are received at the base station. For example, a distant subscriber would send at a higher power level than a nearby subscriber, which would be required to transmit at a lower power, and overall we would have a power management system such that a particular one would not dominate. This is going to be very important in OFDMA, as we shall see. So we've already discussed two important aspects. One is the fact that we have to have some kind of power control. There has to be communication between the base station and the subscribers, where the base station, through a number of transactions, adjusts the power level in the subscriber station such that nearby subscriber stations reduce their power, subscriber stations that are further away increase their power in such a manner to achieve power management and reduce the amount of interference and overload. The other aspect, which is also very important, and this is extremely important in OFDMA, as we shall see, is the fact that packets sent or data sent from subscriber stations have to be received at the base station at the same time. Also, in time division duplex, all subscriber stations will transmit the packets in a way so that they're received by the base station at the same time. This requires communication from the base station to the subscriber stations such that they are synchronized. For example, a subscriber station that is further away has a longer round-trip delay. Therefore, when all subscribers transmit in parallel back during an uplink transaction to the base station, the subscribers that are further away would actually transmit earlier than subscribers that are nearby in such a way that all of their packets are received within a very small time window, or we can say simultaneously at the base station. I will go in depth and describe how this is done in 802.16a, and we will also discuss how power management is also achieved. Another issue that has to be resolved is the effective frequency offset, and that is every subscriber station might have a frequency offset compared to the base station, and the frequency offset from substation to substation is different, so that is also part of the synchronization process, in the sense that through some mechanism and algorithms, the frequency offset has to be compensated between the subscriber stations as the base station receives their packets. Going back to the downlink is a little bit easier in the sense that all subscribers are listening to the downlink from the base station, and the base station can broadcast a packet of information to all the subscribers, and of course the issues are less complicated than in the case of an uplink, and we will go into detail and describe how OFDMA achieves multiple access. That is, multiple users can share the same uplink link and send their information in parallel simultaneously to the base station in a TDD transaction. The procedure for synchronizing, for time synchronization between the subscriber stations and the base station, and also the adjustment of the power, is called ranging, and there is always an initial ranging, an automatic ranging, and subsequently during over a time period there are more adjustments that are done as necessary. Here, this is a paragraph straight out of the 802.16a standard on subscriber synchronization, and what I'll do is just read this right out, seeing how important it is. For any duplexing, that means whether time division duplexing or frequency division duplexing, all subscribers shall acquire and adjust their timing such that all uplink OFDM symbols arrive time coincident at the base station to an accuracy of plus or minus 25% of the minimum guard interval or better. So this is the requirement for time synchronization, and we'll show exactly why this is important and how all this actually works. Okay, we're going to talk about the whole TDD frame in which we do a downlink followed by an uplink from the subscriber stations. Going to go in depth of how subchannels and slots are allocated and how the base station actually sends information to the subscriber stations so they know exactly which set of data regions are associated with their data, and what data regions they have to use in order to send information back to the base station. So a very important topic's coming up. Actually, there's only about 3 pictures that we're going to show that tell the whole story. What we see here again is the base station and subscriber stations. Assume they can be mobile or fixed, assume fixed for now. In a TDD transaction, when you send a frame, what you have is you have first a downlink from the base station to the subscriber stations. So all the subscriber stations see the downlink packet from the base station. So all the subscriber stations are in receive mode. The base station is in transmit mode and sends a packet consisting of multiple OFDM symbols and a preamble, of course prior to the symbols, that all subscriber stations use in order to do channel equalization, acquisition, so forth, carrier offset estimation, correction, etc. We'll talk about the acquisition later. After the downlink, the subscriber stations will know which subchannels and which slots are associated with them, which data regions, and they would commence with a transmission back to the base station with their data. There is a time gap between the transmission from the base station, the downlink to the subscriber stations, and when the subscriber stations turn around and transmit information back to the base station. And that gap we'll discuss is referred to as TTG, which is a transmit to receive transition gap. Also, there's a gap between which the subscribers go from a transmit mode to receive mode before the base station initiates another downlink. As we discussed before, when the subscriber stations transmit back to the base station, they should all have been synchronized through ranging, such that all the OFDM symbols transmitted from the subscriber stations that transmit in parallel are received by the base station in a time synchronous manner, essentially coincidental. They all are received at the same time within a very small window of error, which has to be less, of course, than the guard interval. And we'll talk about that. That's one of the benefits of OFDM, where the OFDM symbol is created through an inverse FFT process. And because of the cyclic nature, there's actually the guard interval, which is better referred to as the cyclic prefix, allows the transmissions from the subscribers to be in error within that window. That is, if they are received within that cyclic prefix time, they can still be recovered with no problem, which is very good quality here. So the time synchronization we're assuming has been done through ranging, initial ranging. So let's go ahead and proceed and see how the data regions are assigned to the various subscriber stations during the downlink process. We now turn our attention to OFDMA concepts. The purpose of the presentation here is to discuss the origins of OFDM multiple access and to present 802.16a OFDMA and go into detail as to how OFDMA works in 802.16a. Let's consider a OFDM transmitter. We have data that is generated, scrambled, goes through a convolutional encoder, puncturing, interleaving, and a mapper. For example, the mapper would take the data and map it to 64 QAM, where each carrier will carry 6 bits. The bits are actually coded. For example, we have 3 1/4 code rate. The serial to parallel converter basically takes the complex constellation points and forms 64 points for 64 carriers, for example in 802.11a. Of these 64 carriers, 48 are data carriers, 4 are pilots, and the rest are nodes, and 1 node at DC, for example. We perform an inverse FFT, and we obtain an OFDM symbol in the time domain. Over here we show time, and we show the results of one inverse FFT operation, where we take the carriers and perform the inverse FFT, and we get one OFDM symbol. We are not including cyclic prefix at this point because this is basically to understand OFDMA concepts. If we look in time, we have one time slot, which is one OFDM symbol, which is 3.2 microseconds in this case without the cyclic prefix. And over here we have frequency, and we have the carriers. Each carrier representing 6 bits for 64.2 QAM or 54 megabits per second. And we're using 802.11a here just as an example. Ignoring pilots, let's just focus on the carriers that carry the data, the 48 data carriers. Now, as more data is generated, the serial to parallel converter assembles another 64 carriers, and an inverse FFT is performed, and we get another symbol, OFDM symbol. Now, as we show in this plot, we actually show 2 symbols, both in time, so we have 2 time slots for 2 symbols, and we also have the carriers shown in terms of frequency. So each point here is a carrier. Now, as more data is generated, again we assemble the data into 64 carriers, including all the nodes, pilots, etc., but focusing on the data carriers. perform an inverse FFT, and we get another symbol. We're showing the carriers and time, where time is showing OFDM symbols, which we refer to as a slot. Now, if we continue this process over a given number of time slots, where each time slot is a OFDM symbol, we will obtain a grid, as shown over here. In this two-dimensional grid, we have time, which is in terms of OFDM symbols, or what we call a time slot, one OFDM symbol, and in terms of carriers. So here we have the first OFDM symbol that was generated, and we're showing it in terms of its carriers. And as we go in time over a fixed number of time slots, we obtain the following grid. This is a very important picture in terms of understanding OFDM multiple access. Consider the next picture where we show a region within the grid. Consider the red region here. Using 802.11a as an example, each carrier here would represent at 54 megabits per second 6 coded bits. Now, ignore all coding for now and just consider the case where we have an OFDM system in which each carrier contains, for example, 6 bits of data. Then within this region shown over here, we are actually transmitting a certain amount of data, a burst of data. We can take the number of carriers times the number of time slots times the number of bits per carrier, and that would represent a data burst. Now here we're simplifying things a lot. In 802.16a, where we talk about OFDMA, we need to talk about FEC blocks, which are forward error correction blocks, which have to be on a certain boundary, and we'll talk about how to arrange the data in order to meet the requirements for forward error correction coding. But for now, just imagine that within this two-dimensional grid, in terms of time slots and carriers, we can have a data region which represents a burst of data. We can also define a region here shown in green, which represents a burst of data. Now imagine that a base station is sending this data to multiple receivers, multiple subscribers. Each subscriber receives the OFDM symbol, performs a forward FFT, and recovers the original carriers. Now imagine that each receiver knows its own data region. So when it performs the forward FFT, it can actually extract the carriers associated with its data region and then decode the data up to the number of time slots allocated for its region. So it knows how many carriers and how many time slots are allocated, and as it performs a forward FFT and obtains the carriers, it then decodes them and it obtains its own data, which was sent to it by the base station. Of course, we're simplifying here tremendously, just ignoring about forward error correction code and just assuming that each carrier contains data. For another subscriber that knows, for example, in advance that its region is this green region here, it will know, for example, what its time slot is, offset, how many time slots is allocated to it, and its carrier offset, and how many carriers are allocated to it. So it will know its data region. And as it performs a forward FFT, it would get its carriers, decode them back to data for this duration, and receive its burst of data. So we can see that if a base station was sending multiple OFDM symbols and the subscriber stations knew in advance what their data regions were, then we have achieved multiple access in the sense that the base station is sending data to multiple subscribers over the same packet. Now the reverse is also true. That is, the subscriber stations can also be told in advance which data regions they can use in order to transmit their data to the base station, and the base station will then perform a forward FFT and knowing which region is allocated to a particular subscriber, then decode the data burst from that particular subscriber. For example, subscriber 1 here and subscriber 2 here. So in an uplink from the subscribers to the base station, we can also use OFDM multiple access as shown over here. Now again, I'd like to emphasize that I have simplified the picture considerably, ignoring, for example, forward error correction coding and assuming that each carrier has, for example, 6 bits per carrier for 64 QAM. And of course, we haven't even talked about how each subscriber will know what data region is allocated to it, or which data region it should use in order to transmit back to the base station. We will cover all of that when we discuss 802.16a OFDMA in detail later on. But here we want to highlight the fact that we've got 2 different data regions that can be allocated for multiple users, and over a fixed period of time, multiple time slots, multiple OFDM symbols, we can actually transmit data bursts to individual subscribers and achieve multiple access using OFDM. The same is true in terms of the uplink, where multiple subscribers can send their data in different regions over a number of OFDM symbols back to the base station. Later on, we will get into the whole idea of synchronization. As you can imagine, there's a lot of issues involved with synchronization, acquisition, carrier offset estimation, channel estimation and equalization, and so forth, which we will discuss in detail later on. For now, we just want to focus on the concept. Now, this slide shows an issue that may arise in OFDMA. We've shown superimposed over here the fading channel frequency response, and we show deep fades due to multipath fading in the channel. And if we consider that we are transmitting from the base station to multiple subscribers, and for now just imagine that we are transmitting to multiple subscribers, but we have a multipath fading characteristic that's shown over here, that each carrier may exhibit a deep fade and therefore loss of signal to noise ratio. Now in actuality, when a base station sends data to multiple subscribers, each subscriber will have its own different multipath characteristic. Here we're showing a single multipath characteristic, but in general, for example, the user associated with the green data region data burst over here would have a different multipath characteristic than the subscriber associated with the red data region here and data burst. But here we're just trying to show the concept. So for example, for subscriber number 1, which is allocated data region in the red, it would exhibit a multipath fading characteristic as shown over here. All of its carriers that it receives in the forward FFT have gone through a multipath and exhibit multipath fading. Some of them could be deep phase as shown over here. So there is a problem in the sense that the carriers associated with a data region can all exhibit multiple fades, whereas in certain regions the degradation is not as severe. So it looks like it's not a good idea to allocate a data region in which the carriers are all adjacent to each other. In fact, it would be better if the carriers within a data region were actually selected from a group of carriers across all carriers such that they are not adjacent to each other, and that is, we perform a permutation of the carriers so that within a data region the carriers are not actually adjacent but have gone through a permutation. Let's take a look at that. In order to analyze this, let's use 802.16a OFDMA carrier as an example. So the idea is that I want to emphasize that multiple carriers can suffer from deep fades. Therefore, within a data region, it is better to actually permute the carrier so that they are not adjacent to each other, similar to what is done in interleaving in 802.11a. But in this case, we are going to actually do the permutation on the carriers. So now we are going to roll into 802.16a and consider its configuration. In 802.16a OFDMA, the number of points in the FFT is 2048, so we have 2048 carriers, which is 2 to the 11. Of these carriers, 173 are null on the left and 172 are null on the right for the guard intervals in the frequency domain. We have a null at DC, and if we subtract these from the total number of carriers, we are left with 1,702 used carriers. Of these used carriers, 166 are used as pilots, with some of the pilots being in fixed locations and some being in variable locations. We'll get into that later. So the number of data carriers is 1,536. Now, in order to achieve this permutation of the carriers, in order to be immune to multipath fading and achieve a more robust communication link, as we discussed in the previous view, the number of data carriers, 1,536, is divided into what we call subchannels. So we have 32 subchannels in OFDMA in 802.16a. Each subchannel contains 48 subcarriers. So if we multiply 32, the number of subchannels, times the number of carriers per subchannel, we get 1,536 as a total number of data carriers. Now the idea is that for each subchannel that contains 48 carriers, the carriers are not contiguous but are actually permuted in order to have better immunity with multipath fading channels. Subchannels are very important because data regions are going to be specified not in terms of carriers but in terms of subchannels. So we'll get into that in a minute. Next, we want to talk about how the permutation is carried out for a downlink. But before that, let's illustrate the concept. So here we have a very simplified picture of multiple data carriers. We have, of course, DC and the carriers in the guard interval in the frequency domain. Now we have a subchannel, which is shown in blue. And for this subchannel, we're showing the carriers in blue. And notice that they are not adjacent to each other. They have been permuted. For subchannel number 2, which is green, also the carriers are not adjacent, but we have a permutation. And also for subchannel number 3, which is in red. So this diagram illustrates the permutation of the carriers so that although we will show a subchannel as being a continuous color, for example, red or green, allocated to a data burst for a user, in reality the carriers are not adjacent to each other but are permuted and actually are scattered about in such a way as to provide immunity to multipath fading channels. So let's talk about the partitioning of data carriers into subchannels, and in this case we will focus on the downlink, which is transmission from the base station to the subscribers. Now this is based on 802.16a recommendation. This formula looks kind of complicated, but it is not actually. Let's explain exactly what is going on here, and we'll give you an example. S is the subchannel number, which will range from 0 to 31. N is the index into the subchannel. So if every subchannel contains, in our case, 48 carriers, so N would be from 0 to 47. S is the number of subchannels, which is 0 to 31. So first we specify a subchannel, and then we want to find out for a given index N from 0 to 47, what is the index of the carrier? So we have 1,536 data carriers. Which one of these carriers belongs to a particular subchannel? So that's what we're computing over here. For example, given the 10th carrier within subchannel number 2, what is its index in terms of the overall data carriers? So this formula is as follows. We have capital N subchannels, which is the number of subchannels, in our case 32, times the index within the subchannel. For example, N spans from 0 to 47, plus this term over here. And let's focus on this term here. Here's where the main permutation happens. Piece of S has an index n mod n number of subchannels. First of all, piece of S itself is a sequence of numbers as shown over here. So piece of S is a sequence of numbers shown over here, and what this means is that for a particular subchannel, we actually shift this permutation base. So we start out with a permutation base corresponding to subchannel number 0, which is shown over here. Now for subchannel number 2, we shift this cyclically to the left. So for subchannel number 2, the permutation base then becomes 2, 8, 16, and 3 and 8 move over to this location over here. So it's a cyclic shift to the left based on the subchannel. For example, subchannel number 1, 18 shifts to the left, 3 then shifts to this position here, and 30 shifts to this position here. So we get a cyclic shift by 1 position to the left. This is the base permutation. So first thing we do is, given the subchannel S, we do a cyclic left shift by the number in the subchannel S. Then once we've done that shift, we take the number n, which is the index within the subchannel for the carrier, again ranging from 0 to 47 in our case, mod the number of subchannels, which is mod 32. So n can go all the way up to 47, and subchannels is 32, so we take n mod 32. That will be the index within the shifted to the left permutation, and then we would pick out that number. For example, if we're talking about subchannel number 1, then we shift everything to the left, and for n equals to 0, we will get 18. For n equals 1, we will get 2, etc. So this is the tricky part here that you need to understand. Then associated with the permutation, we have the ID cell. For example, it could be equal to 2. The ID cell is set by the MAC. So the physical layer gets that from the MAC and is set for a particular cell covered by a base station. For example, it could be equal to 2. Seeding is the C function. For example, the argument is a floating point number. If it's, for example, equal to 3.6, then sitting would be equal to 4. It's an integer. We take that times the cell ID plus the permutation shown over here, as we discussed, and take the sum and do an n mod number of subchannels, which is 32, and then add it to the number of subchannels times the index n, and we obtain the carrier index that is used within the subchannel for the nth carrier within the subchannel. Best thing to do is look at an example. So here we've actually written a C code to implement that expression. We're using a ID cell equals to 2, and we're looking at subchannel number 2. And here we have the computed carrier indexes. So for n equals to 0 through 47, we have the carrier index. Here we show a subchannel. It has 48 carriers, and n is the index within the subchannel. So this, for example, this particular carrier here, so this carrier location here at index 15, for example, corresponds to carrier number 487 from the data carriers. And as we go and look at all the 48 carriers in this table here, we see that we achieve our goal of a permuted carriers, and a single carrier is allocated for a particular subchannel. That is, a carrier cannot occupy multiple subchannels. So this table is very important. It shows that we have achieved our goal of permuting the carriers. None of the carriers are adjacent to each other, and we have within a subchannel carriers ranging from lower index carriers all the way to higher index carriers, and a permutation thereof. So we have achieved our goal in terms of permuting the carriers in order to have a more robust communication link with multipath fading channels with deep fades. A few more important points about the permutation and the partitioning of data carriers into the subchannels. The fact that the ID cell enters in this permutation is very important because when you have a multi-cell situation where multiple base stations are serving subscriber stations, and subscriber stations could be close to each other between the cells, then by using different IDs for the cell, then the probability that the adjacent subchannels and cells will actually coincide is low. There'll be a low probability of a hit in that case. So by using a different ID cell for different cells, then the permutation is such that the subchannels within adjacent cells don't have coincident carriers, and there's less chance of interference between the two. In other words, the probability of using the same physical subcarriers in adjacent cells and sectors is reduced. So that is very important, and each base station will have an associated ID cell for that cell covered by that base station. Also, the n mod operation over here, since n, the index of the carrier within the subchannel, ranges from 0 to 47, and we're taking n mod the number of subchannels, which is 32, so we have 32 subchannels, then n mod 32 ranges from 0 to 31, and we have 32 entries within the permutation base, so we have numbers from 0 to 31 here. Now that we have introduced the concept of subchannels, in which subchannels represent multiple carriers that are obtained through permutation, in the case of 802.16a OFDMA, we have 32 subchannels, and each subchannel contains 48 carriers. So let's look at the grid over here, in which the arrangement is in terms of the subchannels. So we have 32 possible subchannels. Again, we're talking about a 2048 point FFT with 1,536 data carriers, and the data carriers are divided into subchannels. Each subchannel has 48 carriers. In the case of 802.16a OFDMA, a data region is defined in terms of subchannels and OFDM symbols. So here we have the OFDM symbols, and for each symbol we show the subchannels, and in our case each subchannel contains 48 carriers. Now here we are defining a data region for a data burst. To define a data region, we need to specify the subchannel offset and the symbol offset. So we have slots corresponding to symbols, so we have a symbol offset, the total number of symbols, and we have a subchannel offset and the total number of subchannels, and this defines a data region, shown over here. Now, if we look at the carriers within this data region, then they're all permuted and none of them are necessarily adjacent to each other, and we meet our requirements in terms of robust communication over fading multipath channels in this case, and the permutations are based on the description we gave. Here is a very important point. You'll notice that N indicates what we call an FEC block. So an FEC block contains the data for one forward error correcting block, and it spans 3 OFDM symbols and occupies one subchannel. So this is very important. So here we show a subchannel, and within that subchannel there are 3 OFDM symbols, and this constitutes an FEC block for forward error correction coding. Now as we get more data, then we go down in terms of subchannels and fill in the subchannels until we reach the boundary. Now the next OFDM time slot is 3 slots after, starting from the top subchannel within the region, and then as we get more data we move down again and then move across again 3 OFDM slots, and each 3 OFDM slots within a subchannel constitutes a FEC block. So to summarize, in 802.16a, we consider the two-dimensional region shown over here, defined by the carriers which are arranged in subchannels, and we have 32 subchannels, each subchannel containing 48 carriers. We also have the time slots, which are a per OFDM symbol, and within this grid we can define a data region corresponding to a data burst. The data region is defined by a subchannel offset and a OFDM symbol index, or a slot time offset. The number of OFDM symbols and the number of subchannels constitutes then a data region. Here we show a very important picture in order to understand OFDMA. In this case let's talk about time division duplex. Here we have a frame, which is a TDD frame, and as we mentioned before, you have in this region a downlink followed by a TTG, which is the transmit to receive gap, in which then the subscriber stations go from receive mode to transmit mode and transmit back data to the base station. So these two constitute the downlink and uplink, all within one TDD, and this is one frame. After the subscriber stations send their data back to the base station, there's a RTG, which is the receive to transmit transition gap, in which the subscribers then switch over to receive mode, and of course the base station switches over to transmit mode. I'll explain the color codes in a minute. You'll notice that we show a preamble for the transmissions from the subscriber stations during the uplink. There's also a preamble used in the downlink transmission from the base station to the subscribers, and all the subscribers receive this preamble, which is not shown but implied. We'll talk about that a little bit more later. If you look at this picture carefully, you'll notice that there are different regions shown by different colors. Each of these particular regions is actually compiled of a number of data regions, and you'll notice that each data region, the boundaries are 3 symbols, as we had indicated before. Each data region is indicated by a offset in time slot and an offset in subchannel. Like, let's take this region here. We have an offset in subchannel, and we have an offset in the time slot, and a size or length or number of subchannels associated with this particular region here, which is actually data with destination to subscriber number 1. Now, there's one particular region which is always fixed in size and constitutes 3 OFDM symbols using subchannel 0 in this case, which is called the downlink frame prefix. And this actually has a number of information elements in there. In particular, it has the frame control header. And this is sent always with QPSK at half rate and the most robust fashion possible, so that all the subscriber stations can actually decode the downlink frame prefix. This is very important because the downlink frame prefix tells you information about the downlink map and also the uplink map. In particular, it has information about the regions which are occupied by the downlink map. From frame to frame, the size of the downlink map can change. Like if you notice in this side, the downlink map is actually changed size. The reason is that if the data burst for the subscribers changes, then of course the size describe those data bursts also may change. So this is a very important point. Also the uplink map. That's why in this diagram we've drawn them indifferent between the two downlinks. Very important point. I'm not going to go into detail of how these downlink maps are set up. Those will be described later, but actually they're set up through the MAC, passed through the PHY. The downlink map can be actually sent with a higher rate than the most robust rate, and that's one of the pieces of information that is given to the PHY by the downlink frame prefix, which tells the PHY actually what the rates are going to be for the downlink map. And of course that the intention is of course the subscriber stations that receive this information, when they decode the downlink frame prefix, they will know what the rate is for the downlink map and are able then to decode it properly. The downlink map has a sort of a linked list or an array of information elements for each data burst which have destinations to particular subscribers. For example, in this case we have 5 data bursts for potentially 5 subscribers. The downlink map describes these regions, and for each region there'll be a data element describing this region so that the particular subscriber can actually know all about this particular region, where it is in terms of the slots, time slot, and of course subchannel offset, a number of subchannels, and of course what the particular rate or coding is used to send these particular carriers, the data here. Those are all within these information elements which are in the download map. So the download map in this case would have information about the 5 data bursts shown here. Now, as we know, the subscriber stations turn around and transmit their data to the base station right after receiving this information from the downlink. And therefore, each subscriber station must know which slots, time slots, and which subchannel offset and number of subchannels has been allocated to it, so that it uses that allocation to actually send its data back to the base station. Therefore, in the downlink, an uplink map is also sent. So this is very important data right over here. So the uplink map, just similar to the downlink map, actually has a list of information elements, and these information elements actually describe for the subscribers the regions which they are supposed to use to send their data. Therefore, once the subscribers receive and decode the uplink map, then they'll know what rate and what region to use to send their data. So, for example, in this uplink, we're showing 3 bursts, different colors from different subscribers, and these regions here are actually specified in the uplink map. So this makes a lot of sense in getting this OFDMA to work. Now the multiple access comes in the uplink in particular, where we are sending actually with one OFDM symbol, we are actually sending data from 3 users who are simultaneously accessing the network and sending in parallel. All transmitters on these 3 subscribers are active in transmitting data. I'm going to describe that in the next slide in detail. One thing we want to point out is the fact that the uplink also has allocated to it a ranging subchannel in which the subscribers can update their ranging information and give feedback back to the base station. And of course the base station uses the ranging information in order to determine power, for example, and also timing offset. So a lot of that processing is done by the base station, and then another set of information is sent back to the subscribers in which they program those parameters in, so the next time they transmit they'll actually be synchronized and so forth, and transmit with the right power as we discussed previously. In the next slide we are going to describe the actual uplink process, where multiple subscriber stations transmit their data back to the base station, of course based on information they received from the uplink map during the downlink process, in which they know exactly what subchannels what offset, and how many time slots were allocated to them. This is a very important diagram, and we will invest quite a bit of time into describing it and understanding it. And after we've described this diagram and block diagram, we should have a very good understanding of how OFDM multiple access works, especially in the uplink. Here we show multiple substations transmitting to the base station. We're showing the transmit path. We have M subscriber stations, M, for example, 10, subscriber station number 1, subscriber number K, or M, or as we shall refer to them as user number 1, user K, or user M. We've simplified the transmit chain on purpose, and what we're showing is the fact that user K, for example, has been allocated a number of subchannels, and of course, as we know, each subchannel has a number of carriers, for example 48. Given the number of subchannels and the carriers, user K knows exactly what those carriers are, the actual carrier numbers that are allocated to it based on the subchannels, and of course based on the uplink map that was transmitted during the downlink process in the TDD frame. So the uplink map actually tells each user what the offset is for its particular subchannels, and how many subchannels and how many time slots. So the user modulates its data and modulates each carrier with a particular data depending on the rate, for example 64 QAM, particular rate, puncturing, etc. And those carriers are presented to the inverse FFT, and of course they're transformed into the time domain. A cyclic prefix is added. They're converted to analog, and of course transmitted through the RF transmitter and transmitted to the base station. We have to pay very careful attention to what I'm going to say here in terms of how OFDMA actually works. User K has allocated subchannels and particular set of carriers. User 1, for example, is also allocated subchannels and a set of carriers. These carriers are orthogonal between users. That is, at any time, no user is using a carrier which is allocated to a different user. In this sense, they're all orthogonal. All the inverse FFTs, so every subscriber uses an N FFT point FFT, in our case like 2048 point FFT, regardless of the fact that the actual number of carriers that it uses is a subset or much less than N FFT. What happens is the fact that when user K puts data on its carriers, it puts a null or zeroes out all the other carriers that are not in use. Those carriers are actually used by other users. So in the frequency domain, all those carriers are null. And of course, this user actually has to null out the guard intervals, left and right, and they also have to null out DC. But in addition, they null out or zero out all the carriers associated with the other users. So with all those zeroed out, the inverse FFT is performed, and the data is in the time domain, and is transmitted to the base station. Now, as the data is transmitted to the base station for user K, it goes through a multipath environment and is received by the base station. Here we show the signal received by the base station from user K as R sub K of N. User 1 also nulls out or zeroes out all the carriers associated with other users, and only, of course, modulates the data associated with its carriers associated with its allocated subchannels, and transmits that data through the chain, performs the inverse FFT, transmits it, and the base station receives a transmission from user K, user 1, for example, through another multipath, different than the multipath for user K, for example. So every user will have a different multipath channel associated with it. User M also transmits. The receiver at the base station demodulates the summation or superposition of all these transmissions, and as we show here, very importantly, all the users are added up, and as we mentioned before, hopefully initial ranging has been performed and everybody has been synchronized with the correct time offset. And this is a very important point. So going back, for example, if user K happens to be further away from the base station than user 1, then user K transmits first or earlier than user 1. Then user 1 transmits. Hopefully they both arrive at the same time at the base station. And as we discussed previously, for example, they have to arrive within at least a window of 25% of the cyclic prefix or guard interval. And due to the nature of the inverse FFT, the data, of course, is cyclic in an FFT, and we can actually recover the symbols within that 25% of the guard interval with no problem. Going back, you'll notice that each user has associated with it like N sub 1 carriers. So user 1 is using N1 carriers, user K, NK carriers. And if we add up all the carriers used by user 1 through user M, and they're all obviously less than the total number of points used in the FFT. We should also point out that for every user that transmits, they have to allocate pilots for their particular transmission, and these pilots are variable. Their position varies, and where they are depends on the subchannel allocation, the actual data regions that were allocated to the particular user. So that is an issue that we will discuss later, but keep in mind that every user uses pilots that have variable locations that depend on the subchannels. Obviously, since every user goes through a different multipath, has a different carrier offset with respect to the base station, then it has to have associated with it its own unique pilots so that the base station can adjust and track the data and demodulate correctly for that particular user. And by the way, this is a reference to a very good paper, which is a multi-user interference cancellation scheme for Uplink OFDMA, which is theoretical in nature, but does a very good job in highlighting the issues involved in Uplink OFDMA. And this diagram here was adapted with some modifications from a picture in that paper. Let's go back to the transmission, the downlink followed by an uplink. And now that we have a good picture of what's going on with the transmitters, let's go back to this diagram and give some more detail. One thing to notice is during the uplink, every uplink from a particular user has its own associated preamble, so that the base station can actually do acquisition on the preamble for example, burst number 1, and equalize the channel associated with burst number 1, which will be a different type of multipath environment in burst number 2. If we go down here, we see that each user has a different multipath environment depending on where they are in the network. The preamble from the download from the base station to all the subscriber stations is implied, and of course it's throughout the whole symbol here is not partitioned. During the downlink transmission from the base station to the subscribers, there are pilots that are distributed among the carriers, the used carriers. Some of those pilots have fixed locations and some have variable locations, but they do not depend on the number of subscriber stations or anything for that matter. Unlike the case where when we allocate pilots for transmissions from the subscribers during the uplink, those pilots are done on a per user basis and their positions change depending on the allocations of subchannels, both the offset and number of subchannels per that particular user. And of course the base station has to track each set of pilots for a particular user on an individual basis. Another important point we need to point out is that During the downlink, the base station is going to use a particular cyclic prefix size. And recall that in 802.16a, unlike Wi-Fi, the cyclic prefix is not fixed. It has different sizes, and of course the base station can use different sizes. It is up to the subscriber stations to figure out what the cyclic prefix size is and what is being used. And when it does a uplink, it has to use the same cyclic prefix or guard interval that was used by the base station. Let's review the scenarios for multi-user interference, that is interference from other users into the carriers of other users in OFDMA. And one of the issues that we've talked about, of course, is carrier offset. We've also talked about timing synchronization requirements to align the reception of all the symbols from the multiple subscribers at the base station. And we indicated that through initial ranging, the base station can adjust the timing offset for each subscriber so that when they transmit, they are received in alignment. And we mentioned, of course, the 25%, within the range of 25% of the cyclic prefix. Another issue, of course, is power management. We highlighted that a little bit before. And the case is that if in fact all subscribers transmitted at the same power, the nearby transmitters would be received with a higher power than transmitters that are further away. And of course that is not good in the sense that you would have these higher power carriers dominating, affecting dynamic range and also leaking into the carrier slots of the other users. So we have to do power control. And let's go back here, and we basically see that at the receiver, we're receiving the contributions from all the transmitters. And of course, we want to do power management here. And the way that is done is it's similar to what we do for the timing offset synchronization in the sense that, first of all, when a subscriber, go back to this situation, when a subscriber wants to join the network, for example, in this case, the subscriber starts transmitting at a very low power. The amount of power can be controlled by, for example, regulatory requirements that are stored in non-volatile RAM. And they would start transmitting at a very low power and wait to see if they receive anything from the base station. Obviously, if the subscriber is too far away and transmit at a very low power, the base station may not receive it. So the subscriber then increments the power, say by 1 dB, and transmits again. Eventually, the base station will receive a packet from the subscriber station, and once it's demodulated the packet, it can figure out what the difference in power is and will send a response back to the subscriber, in which case the subscriber would adjust its power under the control of the base station. The base station therefore can manage the power from the multiple subscribers such that to minimize the multi-user interference from all the subscribers. So in summary, the factors that influence multi-user interference within an OFDMA system is one of them, of course, is power management. We've discussed that. Time alignment, we've discussed that, where initial ranging, the timing offset is programmed into the subscriber stations by the base station doing the bulk of the single processing in order to achieve that. And of course, we have the situation where every user goes through a different multipath, and multipath obviously causes multi-user interference in a OFDMA. And we mentioned that every transmitter has to send its own, every user sends its own preamble so that the base station can equalize that particular user. And finally, there's carrier offset issues between the different subscriber stations and the base station. And of course, through single processing, the base station has to adjust for the carrier offset. That's where each subscriber station sends its own preamble, or its own set of pilots that are used to also track any residual carrier offset. Here we are going to describe ranging in detail. As we mentioned before, we're going to talk about initial ranging. in which case subscriber stations are going to, for example, join the network. Notice that at any time a subscriber station can be listening to the base station and can receive the downlink from the base station, decode the downlink, and of course get its uplink map. And one thing that the base station is going to try to figure out during the initial ranging, of course, is the timing offset required for the subscriber station, so it can program that into the subscriber station such that all subscriber stations, when they transmit, they have a time alignment when their OFDM symbols are received by the base station. Here we have an example, probably the best way to look at this, and this is from a reference by Shakil Beg from Chalmers University of Technology. And let's take this particular example. We're talking about a system with a symbol time of 64 microseconds, an FFT length of 2048, sampling rate of 32 megahertz. Again, this is an example. Let's assume a cell radius of 20 kilometers. If the cell radius is 20 kilometers, then the maximum round-trip delay is around 133 microseconds. Therefore, if you look at all the round-trip delays that are expected from all the SSs, they can be anywhere from close to 0 to 133 microseconds. If we go back to this picture, so depending on where the subscriber stations are, we can expect delays up to 133 microsecond round-trip delay. The question is, the base station has to figure out, based on a received code, received transmission from the subscriber station, what the actual round-trip delay is, and send that message back to the subscriber station so the subscriber station can program that in and use it in transmissions to achieve time alignment. So the processing is going to be done by the base station, and we're going to describe what that processing is with this particular example. So the time window that the base station has to process in order to figure out what the timing offset is or the round-trip delay is 133 plus 64 microseconds, the 64 microseconds being the symbol time. If we take this time duration, 133 plus 64 microseconds, this corresponds to, at a sampling rate of 32 megahertz, corresponds to 6,304 complex samples. So that's the amount of samples that have to be processed by the base station in order to figure out what the round-trip delay is to the subscriber station and, of course, program the correct timing offset. As we've mentioned, each subscriber station selects a Cdma code, which is, in the case of 16E, is 144 bits long in the frequency domain. And there are from 0 to 255 codes, so 256 codes for 16E, and as we mentioned for 16A it's 48. So each subscriber station is going to select a code. So again, we have for 16E 255 codes, and the codes are 144 bits long in the frequency domain. In fact, if we take the inverse FFT, then they are 2048 samples in the time domain. We have a total received window of 6304 to accommodate the long round-trip delay corresponding to 20 kilometers. And the point is to find the timing offset. So let's go to the next slide. And this picture is again from the reference Shakil Beg. And this is a good diagram because it shows that the base station is going to receive a long time record of, say, 6304 samples. And it has to figure out two things. One is for example, the timing offset. So corresponding to the round-trip delay could be anywhere here. And of course it has to figure out what Cdma code was actually transmitted. And let's take the case where we have a Cdma code. We assume a Cdma code, and we want to find the actual time offset corresponding to the round-trip delay. Then you have to take the Cdma code and cross-correlate it with the received time record. And this is a very involved process in terms of requirements, in terms of multiplications and additions. So you take the Cdma code and multiply it times the received data, then you shift it, of course multiply it and add, multiply and add, and you get the cross-correlation as this window, the Cdma code, is moved across the received data. And as you do this, there will be a case where the received signal would have maximum correlation with the Cdma code, and you will see a peak, and that peak corresponds to, of course, the round-trip delay from which the base station can compute the required timing offset in order to program into the substation in the subsequent response. Due to multipath effects, of course, you won't get a pure impulse. You will get a smearing due to multipath, but nevertheless you should be able to compute the timing offset with the cross correlation with the Cdma code. Now there are ways to perform this computation in a more efficient manner, and I will refer you back to Shakil Beg, who addresses some of these techniques. And of course you can come up with your own techniques. Now this is done with a particular Cdma code. Then you pick the next Cdma code and repeat the process, because the base station has to figure out which Cdma code was sent. So it has to know what the Cdma code that was sent and its timing offset. So this has to be repeated for all, for example, 255 more Cdma codes. As we mentioned, when you have a TDD frame, the base station sends the downlink, and in the downlink there is the specifications for the uplink map over here, so that when the subscriber stations decode this, they can extract the uplink map, and from that they would know what the ranging subchannel is that they will use in order to do ranging and send ranging information. And again, notice that the ranging subchannel corresponds to a particular location which is specified in the uplink map, and it corresponds to a number of time slots or slots of OFDM symbols. So you have both specification in terms of subchannel and slots in terms of the OFDM symbols across in this direction at a time. So this information is available to the subscribers so that they can send the Cdma code within the particular slot back to the base station. The paragraphs that you see here are straight out of the 802.16a specification, and there are a couple of points that I want to highlight, beginning with the ranging process. Obviously the subscriber station, after acquiring downlink, synchronization, and uplink transmit parameters, essentially obtaining this information here, shall choose randomly a ranging slot. Now what is a ranging slot? Again, you have slots over here, and there will be a ranging slot which is chosen randomly by the subscriber, and I will use for example, a binary truncated exponential algorithm to avoid collisions or recollisions. So these are randomly chosen so that substations don't collide with each other. As the time to perform the ranging, then it chooses randomly a ranging code from the initial ranging domain and sends it to the base station as a Cdma code. So for 16A, this is, for example, going to be 48. For 16E, it's 256 from among 256 possible codes. So again, to summarize here, it's going to choose a random ranging slot, and it is going to choose a random code, Cdma code in this case, and it is going to then send that back to the base station within this the data ranges specified during the decoding of the uplink map, this region here. Now, once this is received by the base station cannot tell which subscriber sent the Cdma ranging request, and therefore it has to, upon successfully receiving a Cdma ranging code, the base station broadcasts what you call a ranging response message that advertises the received ranging code as well as ranging slot. So this is very important. The base station essentially has received a communication from subscribers. Through that long, lengthy process that we mentioned, it can figure out what the timing offset is corresponding to the round-trip delay. It can also figure out what Cdma code was used, but it doesn't know which subscriber sent this, so it can't address it to a particular subscriber station. However, the base station also computes, for example, the required power for power control that it has to program into the subscriber station. It has computed the required timing offset to achieve time alignment and other parameters, for example, frequency offset. But it doesn't know what subscriber station actually sent this. So what it does is it actually encodes the ranging code that it has figured out what, for example, it has figured out what the Cdma code was used, and it knows what ranging slot was used. So it sends that to all subscriber stations. Then the subscriber station will look into the Cdma ranging code and identify that it was the one that sent that particular Cdma code, and therefore it knows that this response from the base station is addressed to it. And it also uses a slot. The ranging response message contains the needed adjustments. For example, these are time, power, and possibly frequency corrections, and a status notification. Also, upon receiving a ranging response message with a continue status, which will indicate, the subscriber station will continue the ranging process until it gets a success message. This is highlighted in this figure here, which on the right we have the subscribers, on the left we have the base station. So what happens is, for example, the base station sends a map containing range region information. That is the Uplink Map. Let's go back here. So it's actually sending the Uplink Map. The subscriber actually gets the Uplink Map. Then the subscriber transmits randomly selected ranging code, and randomly selected ranging slot from the available ranging region. This is, for example, the Cdma code, and also a ranging slot from among the ranging region. So it sends that back to the base station. The base station receives the ranging code and, of course, does the single processing necessary to extract the timing offset and also measure the power and compute power corrections. So the base station then sends ranging response with the time and power corrections and the original ranging code and ranging slot. Again, it didn't know which subscriber sent this. So it sends the ranging code and ranging slot back. The subscriber receives the range response message from the base station, checks the ranging code, the Cdma code for example, and the ranging slot, matching the sent value. So if it figures out that it sent that ranging code and used that slot, then it knows that this message is for it, and it receives the adjusts its time and power parameters based on what was sent by the base station. And of course, the state could be continue, in which it goes into the next step, and we repeat sending the Uplink Map, and again the process is continued until the status of success is received, and this shows the complete interaction in order for the subscribers to send data to the base station to actually figure out what the required timing offset correction is and what the power correction is for power control, to send it back to the subscriber. The subscriber would know that it is designated for it if its Cdma code, for example, or ranging code and ranging slot match what it had used in the first place. Here we show the basic configuration where you have the base station MAC, which controls the base station physical layer, the baseband. It sends data to the radio, which is modulated and transmitted through the base station antenna to the various subscriber stations. Of course, this is very simplified and highlights sort of the downlink. Typically between the MAC and the baseband there would be a high-speed bus to send user data, which are intended for multiple users. There will be a handshake and control signals along with the data. Also very important, there is of course many configuration registers in the baseband which are programmed through the MAC, and the baseband uses the information in these registers in order to format the data and modulate. In our case, for the downlink, the base station MAC, the first thing it does is it sets up the downlink frame prefix. Then it follows that with a downlink map and the uplink map message. These are stored in the base station physical layer, baseband, and of course based on the information in the downlink map, uplink map, and in particular the downlink frame prefix initially, the baseband generates the data in a particular format, encoding the OFDM symbols and transmitting them. If we go back here, let's take a look at the format for the downlink frame prefix. This information here, which, as we indicated before, is sent first, is sent with the most robust communication modulation, which is, of course, for OFDMA, 16A is going to be QPSK with half-rate coding both for the inner and outer code. These tables are going to describe the actual content of the downlink frame prefix, and you'll note that the first 4 bits are associated with the rate ID. And the rate ID is a number from 0 to 15, since it's 4 bits. And if its ID is 0, that means that the frame is going to be encoded with QPSK at half rate, 1 for QPSK at 3/4 of a rate, and so forth, all the way to 5, which is 64 QAM at 3/4 of a rate. This rate ID, of course, applies to all the symbols except for the symbols in the downlink frame prefix itself, but applies to the rest of the OFDM symbols in the downlink. The other information is very important, and that is 10 bits are allocated for the number of OFDM symbols and 6 bits for the number of subchannels. We indicated before that for 16A OFDMA, the maximum number of subchannels, of course, is 32. Each subchannel had 48 carriers. And 6 bits, of course, 2 to the 6 is 32. Let's go back to here. So basically, the downlink frame prefix designates the rate that is going to be used for the downlink. It also specifies the total number of symbols, OFDM symbols, that are going to be used, 10 bits, and also the number of subchannels. In this case, we're using 28, and of course, it could go all the way to 32. After the downlink frame prefix, that is followed by the downlink map. And the downlink map, the size of the downlink map, of course, can change depending on how many downlink bursts you have. And so too the uplink map, and its size can depend on the number of uplink bursts. The downlink frame prefix is followed immediately by the beginning of the downlink map message, and then followed by the uplink map message. Now the downlink map message, the structure which is provided here, this is the format, is organized by the MAC layer, and of course, as we mentioned before, transmitted to the PHY. And based on the information here, the PHY organizes the data within the downlink for various users. In this case, the downlink map specifies the regions where the user's downlink burst will reside. Of importance here, of course, is the fact that we contain the base station ID, which is 48 bits. This, of course, is used to identify the base station, and not to be confused for an Ethernet type of address or MAC address. This is the base station ID. And of importance is the number of downlink map elements, N, which is specified here, and it's 16 bits. That's immediately followed by N information elements, which are the downlink map information elements, which specify the whole map for the downlink bursts. Let's take a look at one of these downlink map information elements. This is the format, and basically it's set up as follows. Of importance is the information down here, where the OFDM symbol offset is specified, the subchannel offset is specified, and a number of OFDM symbols used, and a number of subchannels used for the downlink burst, which this information element refers to. Let's go back to the map, the downlink map. Let's take a look at, for example, downlink burst number 1. The information element for downlink burst number 1 would need to specify the offset for the OFDM symbol here, the time slot, and the offset for the subchannel, the number of OFDM symbols, and the number of subchannels. Let's go back here. So basically, the OFDM symbol offset, the subchannel offset, number of OFDM symbols, and number of subchannels for the downlink burst. And here we have, of course, 5 downlink bursts, so the number of elements here would be 5, and this would be followed by 5 information elements describing each region. Similarly, for an uplink map, in this case, one of the more important pieces of information is the uplink channel ID for the particular uplink burst. Again, we have the number of uplink map elements, and each element is defined by an information element. Let's go down and take a look inside. Again, you have the communication ID for the information element, very important for that particular uplink from a subscriber. This communication ID is allocated by the base station. And of course you have again a OFDM symbol offset, the number, the subchannel offset, boosting, number of OFDM symbols, and number of subchannels that are specified. Let's go over here. So the uplink map here basically has the information elements for uplink map. Each information element completely describes the uplink regions. For example, for uplink burst number 2, it would specify, for example, the OFDM offset, the subchannel offset, the number of OFDM symbols, and of course the number of subchannels allocated to that uplink burst. That information is provided in the uplink map here, as we've shown here. So you have the basically the OFDM symbol offset, subchannel offset, number of OFDM symbols, and of course the number of subchannels. Now the uplink map also has a field for the uplink interval usage code, which is 4 bits and has 16 possible values. Of importance to us is, first of all, if it's 12, then that means that it's doing an initial ranging, and 14 is the Cdma allocation information element. Let's take a look at that. The Cdma allocation information element is basically the base station sending information back to the subscribers, indicating that what the ranging code was used by the subscriber. And remember, the codes were up to 48 Cdma code, so that's why this is 6 bits. And of course the ranging symbol used, which as we said was what the actual slot that the subscriber had used in order to send its information. And this is what the base station determined, what code was used, what ranging symbol, and then it sends that back down to the subscriber, of course, with information about the OFDM offset, subchannel offset, number of symbols, etc. for the region. So we've described the basic downlink and how that's organized, and how the MAC actually configures the PHY in terms of the downlink prefix, followed by the downlink map and the uplink map, and specifies how the downlink bursts are to be arranged in terms of the offset in time, the OFDM symbol offset, the subchannel offset, number of OFDM symbols, and the number of subchannels allocated for particular bursts. Also for the uplink map, specifying the uplink bursts, and also particular specifying information about ranging, initial ranging, power control, and so forth, and of course what subscribers used in terms of the Cdma code and the time slot that was used.